Good morning. My name is Kiran, and I work as a director of research at International Fertilizer Development Center. This talk is supposed to be given by Glauco, who is a formulation scientist working at IFDC. Unfortunately, he is unable to come, so he has requested me to join. So I will try to justify the talk. So my talk is about optimizing nutrient synergy through the development of organomineral fertilizers. A brief history about fertilizers in the United States of America. So Muscle Shoals, which is a small city in Alabama, is involved in the development of fertilizers since a long time. This slide gives a small time frame of involvement of IFDC with respect to fertilizer development. So back in 1918s, at the time of World Wars, so US is producing nitrates in a sense to supply ammunition at the time of World War. So after the war, they were not sure what to do with those ammunition. At the same time, in 1926, Wilson Dam was developed to control the floods and to generate electricity in Tennessee Valley. In 1936, to improve the wetlands in that region and to prevent malaria, Tennessee Valley Authority was created to manage floods and to generate electricity. Later, National Fertilizer Development Center, which is kind of like an arm to Tennessee Valley Authority, was established. There were almost at the time I heard 70 to 80 chemical engineers were working in the building, try to develop various fertilizers. In fact, TSPs, DAPs were in fact produced the first time in the world in these buildings. Later, National Fertilizer Development Center was focused on developing fertilizers, keeping US interests in point of view. At that time, in 1974, there was an oil shortage. At that time, the president of the US wanted to share the knowledge of fertilizer development to the developing countries. But NFDC and TBA were focused more on domestic markets and domestic fertilizer production. So at that time, the president of US wanted to create a international organization focused on transferring the knowledge of fertilizer production to developing countries, especially South Asia and Sub-Saharan Africa. So in 1977, President Kissinger has given international organization status to IFDC with all associated immunities and privileges. So one of the priorities for IFDC is to develop better technologies and advanced fertilizer products. The rest of the three are more focused on Sub-Saharan African and South Asian context. So the rest of my presentation is focused on, for a few slides, I will focus on the context behind this presentation and the context behind the project that we are currently handling with the help of funding from USAID, USDA Foreign Agriculture Services in collaboration with the University of Florida and Embrapa from Brazil. And the second part is the context to the same presentation. In 2015, IFDC collaborated with a private company, and at that time they developed an organomineral fertilizers using biosolids and then they used ammonium sulfate and they came up with an ammonium with a organically enhanced ammonium sulfate. So they evaluated it for various nutrient use efficiency characteristics and they published the study. Then that resulted in writing a grant that is resulted in Fertilizer for Life project. So the objective of this presentation is to give you salient features with respect to biosolids and ammonium sulfate project and Fertilizer for Life project. A bit of introduction to organomineral fertilizers. This morning, my previous speakers have made this slide easy to explain. Thank you. So in a sense, synthetic, each option has different pros and different cons. For example, synthetic fertilizers, in terms of just active ingredient and material point of view, the variability of the nutrients is quite low in synthetic fertilizers compared with organic fertilizers, because organic fertilizer feedstock could be varied, and it varies from time, it varied based on the raw material. At the same time, solubility, usually synthetic fertilizer solubility is high. Of course, there could be few exceptions, but in general, organic fertilizer solubility is low, resulting in it takes more time for mineralization, and nutrient release in case of synthetic fertilizers is very high, and it could be low for organic fertilizers. Another important point is nutrient balance. Usually, synthetic fertilizers are developed just keeping plant nutrient composition in point of view. Whereas in organic materials, we need to deal with the availability of the materials that we have, the availability and the nature of organic materials. Nutrient content, this is another important point. For synthetic fertilizers, it is usually high. It can go until like 50%, whereas in case of organic materials, the nutrient content, total nutrient content per ton could be low. Then transportation costs, as my previous speaker mentioned, transportation cost could be very high for organic fertilizers compared with the synthetic fertilizers. But it also depends. For example, if you keep a sub-Saharan African context point of view, where the transportation of synthetic fertilizers is also very high, whereas in that case, probably the transportation of organic fertilizers could be low, because of transportation, it also, we need to consider the transportation from actual production site in the factories somewhere in Europe to a small place in sub-Saharan Africa. Then in terms of soil health, we found numerical evidences for a higher microbial population in organic fertilizers, and subsequent benefits like soil organic matter, carbon concentration, and water holding capacity. Usually organic fertilizers improve all those three characteristics, as we found in our this morning's presentation. Then greenhouse gas emissions, it can vary from organic fertilizers. I don't think we can come up with a blanket conclusion that organic fertilizer application either enhances greenhouse gas emissions or can lower greenhouse gas emissions, because again, the same logic, the raw material and the nature of the raw material and the time of production varies. Contaminants is an issue in organic fertilizers compared with the synthetic fertilizers, usually. And the last one is policies. Usually we have a very well-defined policies with respect to synthetic fertilizers, but I don't think we have that kind of well-defined regulations in case of organic fertilizers. So in a sense, organomineral fertilizer concept is a relatively a new concept. It tried to address the pros and cons of each category, and for example, organic fertilizers, the nutrient concentration is low, but it has higher amount of organic matter. If we combine synthetic fertilizers with organic fertilizers, probably it could be a relatively a balanced. We can address the cons of organic as well as strengths of a synthetic fertilizer, and we can come up with a new optimized new fertilizers. So just a marketing slide. According to a survey conducted by a consulting group, we can forecast a very high market for organomineral fertilizers in the near future. So then this was a study that we carried out with the Cranfield University in the UK. Here, they came up with a paper on strengths, weaknesses, opportunities, and threats with respect to organomineral fertilizers. So again, This morning you have explained in detail about some of these aspects with respect to strengths, with respect to organomineral fertilizers. Of course, it is going to improve soil health. It is a sustainable fertilizer products. Usually, they are balanced products in terms of nutrient composition and carbon. There is a huge potential. There is a potential for carbon sequestration. Coming to weaknesses, traceability is an issue. Unlike in case of synthetic fertilizers, there is a threat, there is an issue with respect to contaminants. And again, cost of production of organomineral fertilizers could be high compared with the synthetic fertilizers. And quality, there are no there are no standard quality criteria for organomineral fertilizers. Unlike organic fertilizers, there is a need to develop and strengthen a quality criteria for organomineral fertilizers. And then transportation is an issue. But there are a lot of opportunities. Is there a scope to get carbon credits by using organomineral fertilizers? That could be an opportunity. Again, there is a lot of talk, and there could be a lot of opportunities in terms of green ammonia. Can we use, for example, imagine down the line after 10 years, there would be like a wide availability of green ammonia in sub-Saharan Africa. We can assume like at a district level, but green ammonia is available. What do we do with that green ammonia? Is there a way that we can transform that green ammonia into fertilizers under the context of sub-Saharan Africa at a smaller scale, at an affordable price, and with a simplified technology? Can organomineral fertilizers, can they give a solution under that context? Then now threats, again, like uncertainty about the availability of the organic materials. And we recently conducted a workshop in sub-Saharan Africa at the time of Africa Soil Health Summit. Then the survey findings resulted that farmers don't want to pay any extra price to organomineral fertilizers compared with the synthetic fertilizers. So at present, probably the technology is not yet mature enough to commercialize it at a wider scale. There is a need, for example, there is a need for certifications, and we need to keep the costs under control. So now I move on to the second part of my presentation about a project that we undertook in 2013. This is like an organo-ammonium sulfate fertilizer production. This was done in collaboration with a company by name Enuvia. So in a sense, they are using biosolids as a feedstock, and then they developed organically enhanced amendment, biosolid amendment. Then that amendment was fed to a pipe cross reactor developed at IFDC, and then in that pipe cross reactor, they injected ammonia and then sulfuric acid, and then they they passed through a sieve, and it was granulated, and from there organically enhanced biosolid fertilizer was developed. They have patented this technology in 2015. So then once the product is developed, then it was screened for its impact on ammonium volatilization, for its impact on greenhouse gas emissions, and then we calculated the amount of the nitrogen that is getting leached in the laboratories, and then we measured its impact on soil productivity, and then greenhouse trials were carried out, and then field trials were carried out. At present, the product is available in the market, so it is already commercialized. So some of the findings from those studies, they're already published in these three manuscripts. In a sense, the developed ammonium sulfate and biosolid product resulted in decreased ammonia volatilization losses, which is in according with the results that were shown this morning, because it took some time for the organomineral fertilizer to get mineralized. Urea hydrolysis was low. Therefore, most of the nitrogen was in ammonium form compared with the nitrate form. Again, we carried out soil incubation studies and what for almost 90 days in the laboratory. And what we found was most of the nitrogen from organomineral fertilizer is in ammonium form compared with the nitrate form. It took a lot of time for organomineral fertilizer to transform into nitrate compared with the synthetic fertilizer. So which is kind of good for the plant. But in the first year, the mineralization rate is low, and therefore probably it could have some impact on plant uptake. And then they carried out field trials in Tennessee with the help of Tennessee Agricultural University. And again, the results are almost similar. In the first year, synthetic fertilizer resulted in higher yields and higher biomass. But in the third to fourth year, almost there is no difference between synthetic fertilizer and organomineral fertilizers. Now, now I'm moving to the third part of my presentation, the current project, which is like a Fertilize for Life project. This project is funded by USDA Foreign Agriculture Services. And this is a very small project, but this is like a multi-institutional collaboration project. We are collaborating with the University of Florida. We are collaborating with LISA for this project, and we are collaborating with Embrapa. The idea is the broader aim of this project is to improve fertilizer use efficiency. The objective of this is because of ongoing conflict or war in the Europe, and many countries in sub-Saharan Africa and many other countries, they are getting impacted because of increase in natural gas prices, and therefore increased cost of production of fertilizers and availability of the fertilizers. So they wanted to reduce the dependence on foreign countries for sustainability point of view. So improve fertilizer use efficiency and reduce reliance on fertilizers coming from overseas markets. And the third and fourth one are related with the sustainability aspects. So we organized this project into 4 working groups. I'm not going to talk about the rest of the 3 working groups, but the third working group, their objective is, their objective is to identify, is to develop new organomineral fertilizers. How we managed is we initially came doing a bibliographic review. We are going to come up with a review manuscript on it. From that, we are trying to, based on the results from the bibliography and based on some brainstorming session, which happened in October last year at IFDC in Alabama. Then we are trying to develop protocols. And then we chose different active ingredients, the available active ingredients. And then we developed a few prototype formulations. And then we are trying to evaluate the developed prototype formulations for their nutrient use efficiency characteristics. And then we want to do some socioeconomic and environment assessments. Coming to organomineral fertilizers. So it is a mineral fertilizer source. what are different options? So we are considering all the options like urea, TSP, ammonium phosphate, or DAP, or potassium chloride and potassium sulfate, and micronutrients. Coming to different organic sources, we considered many organic sources. It could be coming from a dairy industry, birds, vermicompost, or it could be coming from plant-based residues such as soybeans, or insect-based from chitin, etc., etc. But after a few brainstorming sessions, considering the budget that is involved with this project, we are compelled to choose one material as an organic source. So considering the agriculture in the southern part of the United States, we chose a poultry litter as a source of organic material. But we played with the different sources of mineral fertilizers, like urea, ammonium nitrate, and ammonium sulfate, and DAPs. So because the logic behind choosing poultry litter is the scale and availability in the southern agriculture region. What we did in essence is okay, at a bench scale, we took organic residues. We passed, our formulation scientists have grinded that material to certain standard criteria. We used a rich granulation machine. Then we played with the different additives, and finally, I guess we settled for water, and then different mineral fertilizers are added to the same machine. Then it was dried, followed by sieving, and then we carried out a physicochemical analysis and then performance evaluations. Then we are scaling up it at a pilot plant scale. IFDC has kind of like a pilot plants at 3 different scales. Small scale can produce organomineral fertilizers for like a few kilograms per hour, whereas medium scale, it can produce fertilizers from 100 kilograms to 300 kilograms, whereas at a large scale, we have the ability to produce at a wider scale, like 1 tons per hectare. The objective of scaling up these operations before commercialization with the help of industry partners is to identify or to play with the different factors that are involved in fertilizer production. So when it goes to a higher scale, we can come up with an optimized process. So in a sense, we used a chicken litter. Again, we milled it, we milled that material, and then the oversized ones were again milled, and then undersized ones was used to prepare the formulations. These are the few formulations that we prepared in the laboratories. So in essence, we developed like 19 formulations. 11 out of those 19 formulations were developed by scientist Vincius in his laboratory in Brazil, in Brazil, and we developed almost like 9 formulations for US. US. So the first column explains the active ingredients in the developed formulations. The take-home message is, in essence, we used for US-based fertilizer formulations. The focus was more on potassium, whereas in case of Brazilian formulations, the focus is also more on phosphorus in acidic soils. Therefore, they wanted more amount of phosphorus. And in case of Brazil, the crop requirements is like soybeans and corn, whereas in case of US, it is mostly corn. Then all the developed products are measured in the laboratory for their nitrogen, phosphorus, K2O, sulfur content. We calculated the theoretical nitrogen concentration that should be there in the organomineral fertilizer, and then we compared it with the actual nutrient concentrations in the lab through wet chemistry. And then most important one is a physical characterization of these fertilizers. We measured it for It is because we have like 19 formulations. We cannot analyze all these for exhaustively for their physical and chemical characteristics. But our idea is we at a preliminary screening, we quickly screen these prototype formulations for their characteristics. But based on the results from nutrient use efficiency characteristics, before going for scaling up operations, we want to narrow down these 19 formulations into 3 or 4 formulations. Once we fix those 3 or 4 formulations, then we can subject them to in-depth physical and chemical characterizations. In essence, all the formulations are measured for hardiness, because it can have an impact on dust generation at a later scale. So we compared the hardness of newly developed fertilizers with the standard fertilizer materials, and we found that majority of the formulations that are developed in the US labs, they met the minimum threshold hardness characteristics. Then also we measured them for pH, solubility, and moisture concentration, etc. And we are planning to, once we narrow down those prototype formulations, we want to analyze them in detail for various other characteristics. The next step is already an experiment is going on the potential of organomineral fertilizers in reducing ammonium volatilization through this pot experiment. Like a top left-hand side picture, and then we have a setup to quantify amount of nitrate that is going to leach through leaching columns, and then we are going to use LICAR machines to quantify the carbon dioxide, N2O, and methane emissions from the developed new fertilizers. And then the idea is to go for field studies. We hope that we are going to get all the data by December, so that we would be able to submit one manuscript as part of this workshop. So in collaboration with Cranfield University, we carried out a survey in Kenya, in Nairobi. So almost 95% of the participants showed a keen interest in using organomineral fertilizers, but at the same time, 95% of the farmers are not willing to pay any extra money for organomineral fertilizers. That would be the challenge at present that we are facing. So probably when we choose binders, or when we choose the technologies, we need to keep this in mind. We need to keep the cost of manufacturing at a small scale to make it commercially relevant in the market. This is the group that is involved in the Fertilizer for Life project. Thank you very much for your attention.